Your Honor, the committees, Your Honor, our beloved professor and all of our colleagues, good morning. Thank you for attending my thesis defense talk. Today I will present about my thesis that is called implementation of and implementation and optimization of OpenStack-based energy monitoring service. I will briefly go through this online. Start with the introduction and following by system architecture and going into implementation and optimization, and also shows the result of the implementation and optimization and end it by the conclusion. Starts with in Taiwan that we want to have a service to monitor electrical infrastructure to get related information such as how much energy consumption per period of time on building within a campus. But at the same time, we also need some device management to locate it and also manage all of the devices that deployed to support the monitoring status. The current status is commissioning, where a vendor is still doing the installation and testing all the meter in place. All of this service we call it as a smart meter, and we want to deploy the smart meter into cloud, which is the OpenStack, to get the benefits such as we can work from a single endpoint that can be accessed anywhere, that offers flexibility for deploying the cloud, for deploying the VM, the scalability if we want to scale it into multiple VM, and also easy migration if we want to backup. This is the topology of the smart meter. We start from an electrical panel sensed by the intelligent digital meter, or we call it meter. A meter connects to the transmission sub-G module and received by the gateway that also have a receiver for a sub-G. This gateway connect to the internet with Ethernet or LAN. From the internet, we use ThingWorx as our endpoint, as our access point to get to access the smart meter service. But to get smart meter service, we need to have reliability and consistency data. How to get the reliability and consistency data? We also need to have a stable collector, which is we need to ensure that all of the hardware is working properly and can achieve minimum downtime. From these things, what we need to do is to give a report and notification about the devices. So in smart meter we have two devices. We divide into two devices, digital meter and sub-G as one of them, and also the gateway itself. So we need to detect whether these two hardware working properly before we expect to receive the data into our ThingWorx platform. So therefore we will focus on the device management page for this thing. This is the diagram for the smart meter that I told. Divided into three parts: a sensor, a gateway, and also a monitoring and management system, also we call. For the commissioning stage and in the current stage, we need to make sure that the sensor and gateway working properly. All of the 213 devices will working properly without any hitch. So from the monitoring and management system part, we can give a support about the feedback information, to give insight about where is the problem? If a problem occurs, where is the problem located? What is the root cause? For monitoring and management system, we divide it into two big category. First is ThingWorks and the other is OpenStack. For ThingWorks, what we want to do with the ThingWorks is to create the device status and also mail notification. For OpenStack itself, it's related to the deployment of OpenStack, and also we create the API that supporting the data inquiries between ThingWorks and also a database inside the OpenStack. Since we will use ThingWorks as the endpoint, um, I will introduce about the ThingWorks in a brief case. So ThingWorks is an application platform that provides complete application design runtime and intelligent environment. It reduces the time and cost and effort required to build a web IoT application. What ThingWorks offers is rapid deployment, visualization layer, flexible and rapid iteration. So it means that if we have a revision for 2-3 times in the short period of time, we can easily do that and integrate the system to provide complete application design. ThingWorks can be operated ThingWorks can operate, but it needs to use the data. So since ThingWorks need data inquiries, we will create the API here. Also to operate ThingWorks, we need some platform and engineer to customize the function and implement the UI design. And the last thing is to deploy ThingWorks as platform as a service. We need to host ThingWorks in a server. Since we will deploy the SmartCampus in the OpenStack as our cloud platform, I will introduce about the OpenStack. The OpenStack is the open source framework, so it's really distributed under Apache license. It allows administrators to efficiently and dynamically manage virtualization and storage, so user can request computational power, network, and block storage as needed. So in this diagram, we get a high-level overview how OpenStack consolidate hardware resource. We have a horizon as access point, so everything can be handled by the horizon itself. So it is not necessary to go through into the system and call the API itself. We can do everything using the horizon. Horizon will send a command through the API to consolidate and manage the resource pool, such as compute, networking, and also storage pool. And directly send this VM to support the application. So using this ThingWorks, it will eliminate the needs of administrator to manually create virtual machine, network, or storage pool that allows users to create virtual environment and automating the process of virtualization. OpenStack has 3 functional nodes to deploy. The first is master node, which is perform the initial configuration, provisioning, and assigning IP address for the rest of 2. And here is control and compute node. The controller node responsible for public API, web interface, schedule, database server, SHQ, and everything. So the controller relies on in the controller. The controller is the place where horizon lies, and using this API or something, all will be installed in the controller. And OpenStack utilizes the hypervisor to support multiple VMs within a single physical machine. This compute node runs a hypervisor and the compute service. So all of the application, all of our service will deploy only in compute node. In this configuration, we use one master, one control, and one compute node. OpenStack offers two options for deployment: virtual infrastructure or dedicated hardware. For proof of concept, uh, we use deployment in a single machine for this stage to demonstrate that SmartCampus be able to SmartCampus service be able to deploy in the cloud platform that is feasible, and deploy OpenStack infrastructure in one physical machine and its virtualization. So this OpenStack structure, master, controller, and compute node will be rather than a dedicated hardware, it will be a virtual machine. The motivation of this thesis is to build the energy monitoring service on top of the OpenStack in a single machine. This is the system architecture where I design based on the fact that we need stable and steady mechanism that collects and stores the data. Based on this fact, we want to have a simple mechanism to store and to have data flow that could be traced by looking on transmission. The reason is to make debugging easier. So within this, using this architecture, we can easily debugging because we can trace all of the logs when something happens, or we know the problem will happen, or which problem will happen in which sector. So Nginx connected to the internet retrieves the resource on behalf of client, and Nginx will behave like a reverse proxy. So it will forward the package into either ThingWorx, either it's Prometheus, or the API gateway. So for Prometheus in here lies as a temporary database to collect all the metrics data related to the server. This is a special case for our optimization to know that our optimization gives us a positive impact. ThingWorx itself is our endpoint application, and API gateway here will be the router for all of the service that we deploy using a Docker. All of our service is not using monolith. Instead, we use the microservice, which is a decoupled service. So the reason is we create one service that capable to do one thing really well. That will give impact in the management of the service. So by creating microservice, we know that if one service has a error or problem, we can just revise or replace this service with the new one without interrupting the other service. So using the microservices also allows a minimum downtime for data flow to connect with each other. And from this service will connect to our MongoDB that lies in the backnet. After the service, there is an API gateway that I told you as for routing, but not just for our routing, but API gateway will take all the requests from the client and identify which service our API request needed, and also routing the API request to the correct path. API gateway allows us to perform a secure connection by implement the authentication. So all of the authentication, which is we are using the basic authentication, relies on the API gateway, not into the service, which is it will make program more complex, which leads to um, more complex method for replacement the service whenever the service has a problem. So this API gateway will be a single entrance point to the client. Client could be ThingWorks or also the internet, the user that want to consume our API. API gateway will behave as a broker, the flow broker for the data flow information. For the implementation, we start within the hardware. We use ASUS RS720, RS12X, which has 12 bay, but we only using 5 bays HDD that using SAS with the speed of 10k RPM. Each of it has 300 gigabyte, and we use the RAID 0 to achieve the maximum capacity. The reason is that at this stage for the proof of concept, we set aside about the safety, the high availability. We only use the high achieved data capacity to support all of the service. In this machine, it has two Intel Xeon, 16 core each, 2 threads, which has a total 32 CPU. The memory RAM used DDR4 in the speed of 2133, 1696 gigabyte, that is each module distributed evenly for both side channels. And machine runs on normal ambient, which is the temperature approximately between 40 degrees Celsius, and voltage core around 1.7 volts, which is it indicates that no overclock implement in this system, and also it stored into the proper environment. Oh, this is the OpenStack. This is the OpenStack system topology that we are using right now. All of the nodes deployed as a VM, we connect it as using a PXE boot interface, so master can control the controller and compute for the deployment and also the lifecycle. For the internet, each of the nodes will connect to the bridge Ethernet interface. The specification for the three of the nodes using OpenStack Mitaka version 14.04. Hypervisor in compute now we use KVM, which is also the open source and also part of the OpenStack. For the specification, each node master we assign one CPU, memory 4 GB, and storage capacity is 80 GB. Controller we assign for 4 CPU, 14 GB memory, and 220 GB storage. And also for the compute node, we assign all of the rest of the resource pool, which is we assign 25 CPU, 72 GB memory, and also 700 GB HDD. For the master and controller, we set as the minimum amount of the deployment, a minimum requirement of the deployment, OpenStack deployment. As for the computer, we just try to squeeze out all of the resource for one machine, and then assign it as a computer to launch our service. This is the system architecture. This is the system architecture after implementation. The system architecture is top view. We can pretend that as a top view. So the MongoDB, the database that we use, and also the microservice, which we call the services here, and also ThingWorks platform, we deploy as an isolated environment. The reason is that we want to deploy all of our service in isolated environment to achieve consistency in high density environment. Judging from this picture, it's quite high density. If we don't use the isolated environment, we will not have a consistency environment that maybe interrupt the runtime for the program. So within this architecture, we're enabled to establish local connection between each other. So the service microservice will query data from MongoDB and pass the data transmission into the ThingWorks platform using the local connection without going out using the internet, which is related to security itself. For the database, to gather reliability and consistency data, we also have facing a problem about the duplication data, which is from the gateway. We face inconsistent timeliness of the data. So the duplication data can be happen when the same data, the exactly same data, uh, transmit by the gateway into the service, which is will store those data into our DB. So MongoDB using this what is called underscore ID as a key for each data. Since the data transmission from the gateway don't have this underscore ID, it will affect the data writing into our MongoDB, which is we have a MAC address, we have the same timestamp, we have the same matrix data, and it can be stored using a different underscore ID. So this underscore ID will automatically assign by the MongoDB itself to to make a distinction between each data. What we propose here is that we manually generate this underscore ID to prevent the duplication of the data by assigning 12 bytes object ID value that consists of 4 bytes value representing the seconds of the Unix time. 5 bytes is the random value which can be we can fill it as using our, for example, our MAC address and MAC address and gateway address in this 5 bytes, and the last 3 bytes will be the counter starting from random value. Aside from the implementation, we also doing the optimization. The optimization the optimization we are doing is to let the hypervisor feature, one of the feature in the hypervisor, which is called the kernel same page merging, or abbreviation is the KSM. So it make it short. The KSM would enable the system to have a higher density VM. So for example, we only have 4 CPU, but we can deploy a VM using 1 CPU, and we can deploy this VM 5 or 6 VM without any problem. Of course, it would affect the performance, but it still can be run and working properly. The reason is that this KSM will search for the same or shared page memory, so it will collect all of the same memory, and then merge it into one location. So KSM is a memory saving duplication feature. It will prevent any duplication for the memory. The reason is that to enable the higher density of using the memory. But it turns out that if you virtualize many of the same operating system, many memory paths are identical. And given that the operation and application code um, are identical among VMs, so since among VMs can have uh, a value or an amount of the same page, and that same page will be merged into one, that enables into create another VM again. But there is a drawback for this feature, which is to perform the KSM, it took 10% of CPU utilization, which is, don't forget that we have two of the hypervisor in our stack. In level 0, we use hypervisor to emulate the OpenStack feature, the OpenStack nodes into the VMs. But inside the compute nodes, which will lies our server lies, it also has a super hypervisor which has the exactly same features, which is also KSM. KSM will deploy in the compute node. That will make large overhead between compute node and also the hypervisor in the level 0. So what we did is we disabled the KSM here, because the deployment of the VMs in level 1, it's fixed. We only could have 3 VMs after we squeeze out all of the resource pool. So we only have 3 VMs, and we don't need to create another one, because we use the OpenStack, which is all of the VMs that matters would lies in the level 2. So the KSM that enable to have a high density environment still enable in the level 1, but we disable it as in the level 0 to save some CPU utilization. And for the CPU binding, and also for the next optimization that we did was the CPU binding. As for the compute node, which has the largest resource pool, we need to do this what's so-called CPU binding. CPU binding is a binding CPU in the physical CPU bind into the virtual CPU that assigned into the compute node. Without the CPU binding, the compute node will use all of the CPU that vacant randomly. So for example, in this picture, we have a two physical core, that one of them consists 16 CPU, that times 2 total is 32. If we assign the CPU without the CPU binding, the compute node will take randomly, which may be using all of the CPU in node 0, but only use the a few CPU in node 1, which will lead to the imbalanced performance between the physical core. With the CPU binding, we make evenly distribute the resource for the compute node, and allocate a particular CPU and map it into the free CPU in compute node. So by doing this, we will have balance, or almost balanced CPU assignment between node 1 and node 0 and node 1 that will lead stability performance. We also have page the optimization result. We are doing some logger, so we're using the Prometheus as I mentioned before as a data logger, and we use those data to and graph it into the CPU usage, and also we do some benchmark to validate the performance of the VM would be better or not. In this benchmark, we use a bench 0.4.12 that doing one thread calculation for 1000 prime number. So for the implementation, for the optimization result, as we can see, the left side is where we are not doing the optimization. So this is the data from October 18 to October 19. It's less than 24 hours where the system it's not really stable. We can judge from the so the blue line, the blue line that has a higher frequency is where the CPU utilization, and judging by the CPU count. So the x-axis is the time, y-axis is the CPU count. I mean, CPU count is how much CPU occupied for 100%. Since we have the 32, so 32 is the maximum. But in this case, we can see that the performance of the CPU is the trend is keep rising. The trend we can judge by this red line. This red line is the moving average value. So what moving average value is, it calculate the average of 100 data and represent it as a dot using 100 data. So it will it statistically can be visualized about the trend of the graph itself. And for the right side is where the system we already optimize. We do the optimization. This data we took from December 3rd into December 11th. So it's 200 hours of data. And as we can see, 200 hours of data. In 200 hours, we have a pretty stable system. We can see the trend is stable between 3 and 4. In the other hand, before we implement the optimization, we have a significant increasing in CPU utilization until 16 or 18. Until 16, yeah. So, but using optimization, we can reduce and the performance remain between 3 and 4, which is we claim it as a stable one. For this one, we do the testing for booting time. We record the booting time in the layer level 0, layer level 2. In the layer level 2, we have a booting time for the VM. So we want to know it will affect the performance of computational power of OpenStack. As we can see here, the layer level 2, which is the VM on top of the OpenStack, before we do the CPU pining and CASM still enabled, it took 106 seconds to boot one VM. But after the CPU pining and disable CASM, we have 35 seconds, which is it's really a huge improvement. For this graph, we are benchmarking each of the VM. So the reason is we also want to know the performance difference in each layer. So layer we have the result for layer 0, 1, and 2. When the orange line or orange chart is um, without the CPU binding and KSM enabled, and the blue one is after our optimization. As we can see in the layer 0, which is the um, hardware or bare metal, we can say it's more faster without our optimization. It took 11.6 seconds to do calculation for 10,000 prime. As using our CPU binding and disable CASM, it took 12 seconds. There probably zero point 0.6 seconds in difference. But as we move on to layer 1, uh, the performance of our optimization looks better than without our optimization. There's a slightly difference that our optimization give a better performance. But the most significant one is the layer level 2, where all of the service and VMs we're deploying on top of OpenStack. It took 90 seconds for the calculation without our optimization, but using our optimization, it took only 12.7 seconds. But the most important thing is that if we can pull the average graph here using our optimization for performance in layer level 0 into 2, using our optimization, the system performs um, stable, we can say stable decrement, because it's almost negligible. The difference is almost negligible. But without our optimization, the the difference is really huge between layer 0, 1, and 2. So the conclusion is, from our thesis, using our optimization, the system stable running with the CPU count in range 3 or 4, and disabling CASM layer level 0, and implement CPU pinning, the lower CPU execution time. So reference, thank you. I will open the question, a Q&A session start from now.